Welcome! In this session, we analyze three air distribution systems widely used in buildings: constant constant air volume, variable air volume, and dual duct. We will emphasize how each handles part load conditions, ventilation requirements, and the sound level control via terminals. Well, the content of this video, we begin with the air distribution systems, starting from the constant air volume, next the variable air volume, and the last distribution system will be the dual duct system. Then we will talk about their behavior at different loads, and finally we will translate this information to selection guidance and pitfalls. By the end of this video, you should clearly distinguish the main air distribution system types. You should be able to propose a sound definition strategy and select an appropriate air distribution system applying simple criteria. And you should recall the key trade-offs that influence early decisions in design. Well, let's start with a question. Imagine that it's a typical day at 3 p.m. and there are 3 rooms in a building: an open office that is half empty, a meeting room that is filled with people, and a copy print room where equipment is running. How will you deliver conditioned air to these 3 rooms in the building? You could deliver the same amount of air with different temperatures, different amount of air with the same temperature, or blend warm and cool air. Which option seems most likely to keep all 3 rooms comfortable most of the time, and why? Then consider what could go wrong if every room always gets the same amount of air, regardless of what's happening inside. Let's start with the CAV systems. In CAV, the fan delivers essentially constant flow to zones. To meet the reduced loads, the coil temperature or reheat is adjusted, which can increase energy use at part load. The approach is straightforward and can fit spaces with relatively stable loads and modest zoning needs. Now about the VAV. VAV achieves part load by reducing some airflow via a terminal. This terminal can be a damper or fan power unit, while the VAV system holds a coil, leaving conditions suitable for latent control. Minimum flow is maintained to satisfy outdoor air and circulation needs. And reheat is minimized because temperature is not the primary control variable at higher loads. Then talking about the VAV terminals, also known as VAV boxes, are some level HVAC devices that regulate the volume of conditioned air entering a space by modulating an air damper. Throttling boxes use only a damper that modulates the primary airflow in response to some cooling demand. This approach reduces first cost because there is no internal fan or induction nozzle. The device is essentially a controlled restriction. They are common and rely on static pressure. There is the upstream pressure maintained by the air handling unit. So these throttling boxes, they rely on this static pressure to drive airflow through the terminal as the damper position changes. Induction terminals are jet induction devices that accelerate primary air through a nozzle to entering room or plenum air for mixing at the terminal. They require higher upstream static pressure to produce the induction effect. Because of this dependence on upstream pressure, they increase central fan power relative to throttling boxes at comparable flows. Then we have fan power boxes. They incorporate a local fan to improve mixing between primary air from air handling unit and recirculated air from the sun or plenum. This helps maintain air motion and mixing at low primary flows, but local fan adds sound. A dual duct HVAC system has two separate air ducts, one for hot air and one for cold air, to provide conditioned air to different zones within a building. Dual duct systems distribute hot and cold air in parallel and mix them at the terminal to meet zone requirements. Some implementations deliver constant volume to zones while modulated central coil flows to control deck temperatures. The approach can offer responsive control but may increase energy use due to simultaneous cooling and heating effects in mixing. Then we will talk about part load behavior. This term refers to how an HVAC system operates when it's not running at its full capacity. The CAV for these systems, the fan always moves a constant volume of air, even at part load. To meet the reduced cooling or heating demand, the system often relies on reheat, meaning it cools the air and then adds heat back to it to reach the desired temperature. This is generally an inefficient method. Then we have VAV systems that are designed to be more efficient at part load. They reduce the fan airflow in direct proportion to the reduction in heating or cooling demand. By lowering the fan speed, they save significant energy. They only use reheat when the airflow is at its minimum to provide final temperature control. These systems handle part load by shifting the mixing ratio of hot and cold air. I'm talking about the dual duct systems. Instead of reducing total airflow, they simply provide more cold air or less hot air, or vice versa, to a zone. While this provides very fast and precise temperature control, it carries the risk of a mixing penalty, which is the energy waste that occurs when the heated and cool air streams are combined, effectively cancelling each other out. For selection of the mentioned air distribution systems, consider the usual match the system to load variability and sound design complexity. Choose CAV for stable loads, simple control needs, and limited number of zones. This system is suitable for retail spaces, classrooms, or computer rooms, where the heat load is relatively constant and there aren't many individual zones to control. Choose VAV for diverse variable loads with multiple zones. VAV is prevalent in offices and similar buildings because it accommodates diversity efficiently. Finally, talk about the dual duct. They can serve challenging response needs, must be designed to manage pressure and mixing losses. This system is a good choice for hospitals, laboratories, or research facilities, where different zones may have simultaneous fluctuating and critical heating and cooling requirements that need to be met quickly. Talk about common pitfalls in these designs. Terminal choices drive upstream pressure needs. For example, induction devices require explicit duct pressure. In the VAV systems, the minimum flow could be set too high, demanding unnecessary reheat to not cool the sound too much. However, we also need a minimum flow to safeguard the indoor air quality. Dual duct sequences must be turned to avoid sustained simultaneous heating and cooling. Finally, for this video, let's recap some key takeaways. Remember that the control variable, temperature, airflow, or mixing ratio, defines each system's strengths and weaknesses. Most operating hours are part load, so the control strategy there dominates energy outcomes. Specify terminals with full awareness of pressure, noise, and maintainability implications. Finally, I invite you to continue learning and reviewing other topics. You could look up information about the concept of static pressure reset. This concept is used to reduce central fan power at per load while keeping terminals stable by trimming duct static as loads fall. You should explore the idea of supply air temperature reset. This concept is used to cut coil cooling and reheat when loads decrease while still meeting indoor quality and comfort constraints. You could read about the airside economizer. This concept is used to increase outdoor air intake under favorable ambient conditions to lessen mechanical cooling, with attention to humidity limits and minimum outdoor air requirements. Thanks for watching this video.